Welcome to the chapter on dynamics. We're going to start off with a discussion about kinematics, which is the study of motion regardless of the forces that cause that motion to arise. Once we get to dynamics, we're dealing a bit more with the forces that drive that acceleration. But kinematics is really just the analysis of position, velocity, acceleration, and time. And the first topic we'll cover here is constant acceleration. There's a set of equations that we can use to analyze both linear and circular motion. There's separate sets of equations with different variables, but they're very similar, and we'll talk through that here. And these equations will give you a pretty big bang for your buck. We're kind of putting together a bit of what you may remember from calculus and also physics. So kinematics draws heavily on both the math and the physics that you would have learned prior to getting to this. Now, we're doing this program a little bit out of order. We could do a lot of the underlying math first as a refresher before we start using things like derivatives. But I really wanted to focus the course on the most important topics that are going to come up the most frequently earlier in the program, which means we'll be covering more of that basic math later on. So feel free to use this out of order. If at any point you're uncomfortable with some of the foundational math that we're covering here, you can get some of the background you need by skipping ahead to the math section. But I'll do my best to cover enough of it so that it makes sense as we go along. So let's start by talking about linear motion, where we have a particle that's moving along the same line, and the independent variable is time, and the dependent variables are the position, the velocity, and the acceleration. So as a general statement, before we get to the point where we're talking about constant acceleration, we should define what we mean by velocity and acceleration generally. We can say that the velocity is the change in position per unit time. So in calculus terms, we would say that's ds dt, where s is the displacement and t is time. Now, what is displacement and how does that differ from distance? Well, distance is like the odometer on your car. If you go and you make several stops, you go from A to B and B to C and then back to A, your total distance is what your odometer would read. It's all of the accumulated distance adding up those individual segments. But displacement is the net difference in how far you've gone. So if you return to point A after making several trips, your displacement is actually zero. So displacement is the net change in position from some starting position. And we want to make sure that when we use the variable s, we know that we're talking about displacement and not strictly distance. So that's our definition for velocity. And then our definition for acceleration is the change in velocity with respect to time. So dv dt. Now those general statements are always true regardless of whether it's constant acceleration or not. But when we have constant acceleration, dv dt is a constant. So that gives us actually our first equation. It's not much of an equation, it's sort of an obvious statement, but we're saying that the acceleration as a function of time is just a constant, a sub 0. They're saying the initial acceleration. And really, it's not a function of time because regardless of what value we put in here for t, it's always going to be that constant a sub 0. And you almost don't need the subscript 0 to say that it's the initial acceleration because the acceleration is not changing. So we could just call this a, but I do want to be consistent with the reference handbook. So I'm going to write it as a sub 0 with the understanding that is our constant acceleration. And now we can define the velocity. And I'm going to write it in a little bit different order than they have in the reference handbook. I'm going to start with the initial velocity. So the velocity as a function of time depends on the initial velocity plus the acceleration times the amount of time that that acceleration has had to exert itself on that initial velocity. What is that amount of time? It's whatever the time is now, t, minus the initial time, t sub 0. Hopefully that makes good intuitive sense. If you're driving in your car and you're going 30 miles an hour initially and then you accelerate at some constant acceleration for several seconds, then it's the product of that acceleration and the amount of time that you did it that gives you the additional velocity on top of what your initial velocity would be. If it's deceleration, then this constant a sub 0 would be a negative number and we'd be subtracting. So that gives us our acceleration and our velocity. And now we can write an expression for the position, s as a function of t. And the position depends on the initial position, s sub 0, plus, very similar to this, the velocity initially, so v sub 0 times the amount of time, t minus t0, plus the initial acceleration times the amount of time squared over 2. Sometimes you'll see this term just written as 1/2 at squared, but we're actually using t minus t sub 0 to signify the total amount of time. So if you have the amount of time since the initial time, let's say it's 3 seconds, then that's what you're plugging in every time you see this t minus t sub 0. So you may see shorter versions of these formulas written in some locations, but this is how they write it in the reference handbook. So I want to stay consistent with that. So these three formulas will get you pretty far, but there's one more that is often forgotten and is extremely useful, so we really don't want to lose track of this one. It's the only one that doesn't involve time. Well, I suppose the first one doesn't because the acceleration is constant. But this one is a way of relating the initial and final velocities without the use of time. So it comes in very handy. And it says v squared, and they don't use a subscript here, but you could also include a subscript f here to signify that it's the final velocity. But I'm going to leave it the way the reference handbook shows it. I just want you to know that this signifies the final velocity at the end of the time. Velocity squared equals the initial velocity squared plus 2 times the constant acceleration a sub 0 times the change in the displacement, which is s minus s sub 0, where s is the position at the end of the time and s sub 0 is the initial position. So final position minus initial position equals displacement. Sometimes you'll see this equation written as v final squared equals v initial squared plus 2ad, where d equals the total change in displacement. So there's a couple of different ways this might show up, but if you understand what these variables mean, you won't get tricked up by which variables they choose to use or where subscripts are and are not included. The real key to getting your head around these problems is to actually solve practice problems that involve kinematics, apply these, get used to them, get comfortable with them. And like I said, these equations will give you a lot of runway. They are the 80-20 solution to all things kinematics. We're going to cover a few other topics, but these will definitely come up. And if you're not comfortable and confident with these ideas, it will probably be exposed someplace or another. And now we're going to cover a similar set of equations which describe circular motion. And another term that's sometimes used for circular motion is angular motion. So if you hear that, that's the same thing. And everything that we're about to write is analogous to what we already wrote for linear motion. So if you ever get confused about this, just return to the comfort of the linear motion equations and then replace the variables with the circular motion variables that we're going to use instead. And hopefully by matching that pattern, your understanding will follow from there. So in just the way that we define the velocity as the change in position over the change in time, we're now going to define the angular velocity, and that gets the Greek letter omega, which looks like a small w. The angular velocity in general is defined as the change in the angular position, theta, over the change in time. And just so we have something graphical to look at too, here we're talking about linear motion. We're basically just moving back and forth on a linear axis. So we can draw the x-axis and say positive is to the right and negative is to the left, something like that. When we're talking about circular motion, we have to think about a circle and some initial position. Here we can have an origin like this and just say it's a point. Here our origin will be some location on that circle. So maybe we'll just say it's here. That's 0 degrees. And then we're going to be rotating from there. So that would be our initial position. And then we can define a direction like this that we're going to rotate to some new position through some angle theta. So if that's our general definition of angular velocity, then angular acceleration, alpha, equals the change in angular velocity with respect to time. So those are general statements, just like these are general statements. Those apply even when it's not constant acceleration. But when it is constant acceleration, then we say that alpha as a function of t is a constant, alpha 0, constant angular acceleration. So it really doesn't matter what the time is, no matter what value we plug in for t, we're going to get this constant angular acceleration, alpha sub 0, out. Then we can express the angular velocity as a function of time. It's going to be the initial angular velocity, omega sub 0, plus the constant angular acceleration, alpha sub 0, times the change in time, t minus t0. And then we have the angular position, theta, as a function of time, is the initial angular position, theta sub 0, plus the initial angular velocity, omega sub 0 times the change in time, t minus t0, plus the constant angular acceleration, alpha sub 0, times t minus t sub 0 squared over 2. And now you can see how these angular equations are perfectly analogous to the linear equations that we had. It may not be as intuitive to think about things when they're rotating as opposed to just when they're translating along a line. But when you apply these equations, you'll find that that intuition that you formed from the linear version, when you go to apply these, it'll fall directly into line. And lastly, we have the equation that omits the time and allows us to relate the final angular velocity to the initial angular velocity. Angular velocity equals, and remember you could put the final here if you want as a subscript, but you don't have to. They don't do that in the reference handbook, but I like to remind you that it should be there. It's the initial angular velocity squared plus 2 times the constant angular acceleration times the difference in position, which you could say is the angular displacement. So the initial angular position theta minus the original position theta sub 0. And that's an introduction to the constant acceleration equations.